Fatal traffic accidents like this one have thankfully become less frequent in the UK over the past few years. But in 2011, 15% of these accidents involved drivers under the influence of alcohol, and that figure has begun to rise. Having fast, accurate technology to detect drivers with illegal blood alcohol levels is an essential for police in their fight to bring these figures down again. Even a small amount of alcohol inhibits brain function, increasing reaction times and impairing judgment. In some cases, 1 pint of strong beer may be enough to raise the blood alcohol concentration to the legal limit of 0.08%. Before breath tests were available, measuring blood alcohol concentrations accurately involved a time-consuming and invasive blood test. However, alcohol in the bloodstream passes out into the air in the lungs in a reversible process. Because the equilibrium constant for this process is constant at a given temperature, the concentration of alcohol vapor in the air exhaled from the lungs will depend on the blood alcohol concentration. After any accident, a police officer will require the drivers involved to blow into a portable instrument known as a breathalyzer or intoxilyzer. This uses a redox reaction to measure alcohol vapor concentration. If the concentration is above the legal limit of 0.08%, the driver will be taken to a police station where an even more accurate measurement will be obtained using quantitative infrared spectroscopy. The ethanol molecule contains OH, CH, and CC bonds. Because of the different electronegativities of the atoms involved, OH and CH bonds possess electrical dipoles. This means that they can interact with and absorb electromagnetic radiation. Electromagnetic radiation consists of vibrating electrical and magnetic fields. The frequency of the vibrations varies enormously between the different parts of the electromagnetic spectrum. The part of the spectrum which is absorbed by vibrating OH and CH bonds is in the infrared part of the spectrum, with a frequency of about 10 to the power of 14 Hertz. The different bond strengths and lengths of the atoms involved in CH and OH bonds mean that they will each be vibrating at different fundamental vibrational frequencies. Absorption of electromagnetic radiation of these frequencies will excite the bonds to higher energy levels. The absorption of radiation by different bonds is shown in this infrared spectrum of ethanol. In the breathalyzer, there is no need to measure the absorption over the full range of frequencies. Instead, the absorption due to CH bonds at around 2,961 wave numbers is measured, along with a baseline measurement in a region of the spectrum where ethanol does not absorb radiation. The amount of absorption at these frequencies will be proportional to the concentration of ethanol molecules in the sample, according to the Beer-Lambda law. By calibrating the device against standard ethanol vapor concentrations, a very precise measurement of the ethanol vapor concentration can be obtained. Accurate, reliable infrared spectroscopy has enabled rapid testing of drivers, leading to effective prosecutions. With increased traffic density and the possibility of lower alcohol levels being introduced, the need for rapid, reliable, and accurate testing is certain to be maintained.